All right, so good morning. Today we're going to talk about valence electrons. Some of this is probably going to be a review. You may have seen some of it in biology as well with some of the diagrams we're going to do. But we're going to quickly review valence electrons, which is one of our last trends of the periodic table. Like I said, it is something we've talked about a little bit at this point already. But it's going to be really important when we go into talking about bonding after spring break, because the valence electrons are the ones that are going to interact and bond and are involved in reactions when they happen. Since they're the ones that are going to be interacting as two atoms come close to each other. So as a quick review, remember that valence electrons are the electrons that are in the highest or outermost energy level of an atom. So when we look at something's electron configuration, like aluminum and selenium, we can see here, for example, that aluminum's highest energy level is energy level 3. It's got 3 s orbitals and 3 p that both have electrons in it. And for selenium, its highest energy level is the 4. Not just the 4 that it ends in, but we know that it also has the 4s orbital as well. So the valence electrons are all of the electrons that exist in that highest energy level. So for aluminum, we see that there's a total of 3 valence electrons, 2 from the 3s and 1 from 3p. And then we have, for selenium, we have 6 valence electrons, 2 from the 4s and 4 from 4p. So if we use the electron configuration like that, we can find the number of valence electrons for any of these different atoms. Now, when it comes to doing bonding, we're going to use a model similar to a Bohr model, but it's a little bit more simplified. It's called a dot diagram, or sometimes called a Lewis dot diagram. And these are something that you most likely have drawn in biology before, where in the center of our diagram, we have the element symbol. Here I put the letter X just to represent any element. But if this was potassium or gallium or any of these examples here, you would have that element symbol just directly in the middle of that diagram. Now, those numbers that go around the outside here, those are referring to the valence electrons of those atoms. So when we have potassium, we're looking at its highest energy level here. It's energy level 4. It has 1 valence electron in that orbital. So in a dot diagram, we use a dot to represent the valence electrons of that atom. The first valence electron usually goes up here at the top. So that is the entirety of the dot diagram for potassium. For gallium, we're looking for its highest energy level. We see energy level 4p is what it ends in. But remember, 4p is not the energy level, it's energy level 4. And it has another energy level 4 here as well. So in total, it has 2 electrons there and 1 here for a total of 3 valence electrons. So again, using the guide up here in the top left corner, our first electron we generally place at the top, the second one on the right, and then we just kind of work our way in a circle around the atom to get all of our electrons. For arsenic, again, we end at 4p3. We notice that our highest energy level is energy level 4. It also has 4s2 for a total of 5 valence electrons. So we have 1 at the top, 2, again, just following that model on the top left corner, going in a circle around the element. Once we get all the way around, we do end up starting to pair up. So we get to this point here. And then lastly, for krypton, again, looking for the highest energy level. We're skipping the D block again because it is not at the 4th energy level. Krypton has a total of 8 valence electrons. So for its dot diagram, 1, 2, 3, 4, 5, 6, 7, 8. And that's it.